Okay. Good morning, good evening, good afternoon. Uh, I'm John Glass. I guess I'm your host today for our third Minimal Cell virtual workshop. And I'm thrilled to have so many of you here. I can see we're up to 44 people, which is great. Our field keeps expanding, and I'm hoping to just let's get into it. By the way, I'm John. I feel like I know almost all of you. I didn't attend the recent Mycoplasma, the International Organization of Mycoplasmology meeting in Osaka that I know many of you did, and I understand it was fantastic. And I so wish I could have been there where some of these things were talked about, but our community. So our community, let me start with my slideshow here. Uh, I like to begin dramatically. That worked better than it did last year. So the reason we exist is 7 years ago, the JCVI published our paper about the minimal bacterial cell. And in the intermeeting period, we have had 55 publications, or probably more. This was just a search of PubMed, and I know there were publications that it didn't pick up, 18 in the last year. And the great thing about publishing this thing 7 years ago, and I had hoped for but wasn't expecting how well it's worked out, is we published this thing and then people have started showing up wanting to be part of our community where we are trying to get to use the minimal cell for first, I think, to understand the first principles of cellular life, but also to think about there are also people in our organization, our loose organization, that are using it for many more applied applications. But I know now that there are more than 70 academic and industrial groups that are using the JCVI minimal cell, which I think is really terrific. And my suspicion is that there will be more. I'm spending too much time doing material transfer agreements, but even that's getting easier these days. And so again, why are we doing this? Well, I look at it, as I said, that this is our organism is a tool to investigate the first principles of cellular life. This idea that if we can have a cell where we understand everything, then it may be possible to build models for that cell and more complicated cells. But the idea of this thing, back to Richard Feynman's quote, what we cannot build, we cannot understand. Well, if we can build a cell, we can really get so we can understand things. And so I'm also seeing some new things that Daniela Bittencourt is going to talk about today. The idea of using JCVI SYN3B as a potential therapeutic agent. So a lot of these things are really exciting to me. In the last year, so there are groups that I was completely unaware of doing minimal cell work. My paper search things failed me a little bit. So, and I failed to get in touch with them late last night when I was counting the number of papers about the minimal cell. There are groups in Europe, in the US, that are computationally using the minimal cell as a model and have published on this, and I was completely unaware of their publications. So I'm going to try to loop them in next year. I'm also excited to say that I was contacted by Alex DeMarca at New York Structural Biology Center, and he is a cryotomographer. And I've given him the minimal cell, and so he is going to be making cryotomograms of the minimal cell with the goal of finding where all of the proteins are in the minimal cell, not just ribosomes, but small proteins and protein complexes based on predicted structure of these proteins using some of the advantages that we've had from new software like AlphaFold. So these may be new data sources that we'll have next year, giving us an idea of the distribution of proteins in the cell and potentially where proteins of unknown function, what they're holding on to. I'm seeing more and more literature that is giving us clues about the functions of some unknown proteins. Groups in Spain, and James Pelletier and Ronald Rodriguez are going to talk about this next Tuesday, have shown that a Mycoplasma pneumoniae protein has a completely never seen before folding structure. And they hypothesize that it is a cholesterol transporter. We have a close ortholog of this, and this may be another protein that we had previously no idea what it was doing, that now we may have an idea what it's doing. The folks at the University of Illinois, in their flux balance computational model, predicted that for the cell to grow at the rate that it does, it has to have a transaldolase protein. And we see nothing in the minimal cell that looks like a transaldolase, but we tried an experiment in my lab where we put a Bacillus subtilis transaldolase into the cell, then did a transposon bombardment and identified a gene, totally unknown function, that doesn't look at all like a transaldolase, that previously was quasi-essential and now became non-essential. And so we're going to be doing, we're going to make the protein in E. coli and test to see if it has transaldolase activity or what its activity is. But I envision that we've gone from 149 proteins in 2016, a third of the proteins this cell makes that we didn't know what it does. And now we are moving below 80. And so this is real progress, and I think we're going to see a lot more of this. So I'm really excited about some of these things that are going on with the cell. It's 5:10 now, last housekeeping thing. I've given everybody 15 minutes for each talk. We should be finishing up right at 5 hours after we start today, if we go on scale. If you go faster than 15 minutes, that's completely okay. If you're having any trouble connecting or doing anything, you can contact Tim Stayes, who's going to be online the whole day. And I will be monitoring your speaking time, and I will let you know once you go past 10 minutes if I don't see that it's obvious that you're wrapping up.